let's suppose that we have an object moving at a velocity that's not a constant, like where we talk about 60 miles per hour. This particular case, the velocity depends on the particular time you're looking at the velocity. So let's pretend like the function that describes the velocity at any time would be t squared. So if t was 0, you'd have 0 squared. If it was 0.5, you'd have 0.5 squared. At 1 second, you'd have 1 squared. And at 3 seconds, you'd have velocity of 3 squared, or 9. If we wanted the total distance traveled from 0 to 3, we need to come up with a way to get an answer for that, and we're going to use the rectangles, the approximations. There's 3 styles. The first style would be where you use the height from the left side of the interval that you're looking at. For example, if I started at 0, I would use the y value at 0. Then if I use the base of these little rectangles as like a half, then I'd want the y value at a half, the y value at 1, the y value at 1.5, at 2, and at 2.5, and that would give me 6 rectangles. The other possibility is to have a midpoint as the x value, the t value, to generate the particular velocities. So then you would use, like, at a half, what's the y value at half, what's the y value at 1, what's the y value at 1.5. So then we'd be using the middle of the intervals. And the last option would be is if you use the right-hand side of each interval. So now you're looking at the first one having a height at the half mark, and the second one would be the y value, or the velocity value, at 1, and finally the 6th rectangle would be the y value at 3, which is v of 3. Later we're going to find out that this approximating is fine. This one looks like it's going to give me 6 rectangles that add up less than what I want. This one looks like it could be close to the what I want. And the one over here, when I add up these 6 rectangles, obviously we're going to get an answer bigger than this area under the curve. Well, we're going to find out that there's something called an integral, and the integral will do this for us. It'll give us the exact value. It's this symbol. That's really an elongated S for sum. We're going to use a sum here. It's an integral sign. And what you do is you find the ancestor to this. In other words, what function had this as a derivative? If you look at 1/3 t cubed, its derivative would be t squared. And that's actually the function that we use to get the total area exactly. And you plug in the top value into this ancestor, then you plug in the lower value into the ancestor, and you subtract these two answers, giving us an exact value line, and we'll see that later why that actually works.